So now, Reyonld is a grad student at UC Berkeley in the AmpLab, and he is the lead on Shark, which is a SQL component on top of Spark. And he will also be around, like the rest of us, as TAs during the afternoon session.
All right, thanks, Andy. You guys can all hear me okay? Yes, all right. So in the next sort of 20, 30 minutes, I'm going to tell you more about the Shark project. And if there's nothing you're going to take away today, I hope one thing you're going to take away is the name. Shark comes from basically taking the H in Hive and then put it in Spark, replacing the P. So this is how Shark comes. And since we're playing the game of show of hands, I did this last year at AmCamp as well. How many of you can sort of read this code in 20 seconds, tell me what is this doing? And then put up your hands if give it 20 seconds. All right, got one hand. Two, it's a few. OK, and now try the next one. How many of you look at this SQL query in 20 seconds, tell me what it's doing? Oh, wow, I got one hand up right away. OK, and I think the point of the exercise is that majority of you actually will be able to tell what the SQL query is doing, and maybe even able to write the SQL query in less than a minute to express something that's much harder to comprehend if you rest it strictly in Hadoop MapReduce. And going beyond that, so there's a lot of talent in SQL, understanding SQL and writing SQL, but also in terms of machines, there's a lot of programs that use SQL as basically the narrow waist for query processing and data analytics. For example, you have Tableau, you have MicroStrategy, you have a set of other tools that might be written by your own scripts that actually use SQL to access data. And that's why we started the Shark project in the AmpLab, that we want to enable sort of a lot of the SQL applications to actually run a lot faster and empower those users too. In the remainder of the talk, since I'm between you and lunch, actually, there's one more talk after me. I'll try to speed up the talk and make up the time. The first, I'll tell you briefly what Hive is, and then introduce Shark project, and then tell you how you can use Shark, and at the end explain how Shark is implemented and why Shark's able to bring you some of the benefits that other systems can't. So how many of you know Hive, have used Hive before? About half. OK, so Apache Hive is it's another open source project that's in the Hadoop ecosystem. And what it does is essentially compiles SQL down into Hadoop MapReduce jobs. And it also puts a structure and schema onto some arbitrary data that might be semi-structured or unstructured, stored on HDFS. And it's very popular. If you look at a lot of the Hadoop deployments, actually majority of the Hadoop jobs are generated by Hive. And especially if you go to Facebook, there's one extreme of it. Over 90% of the jobs are actually generated by Hive, or at least used to. And compared with a lot of the existing data warehouse systems, Hive has a few different, I think, key benefits. One is scalability. It's extremely scalable because it's built on top of Hadoop MapReduce, so you can actually run Hive on thousands of nodes. And because of this scale-out nature, when you run out of capacity, you could actually just add more machines to it, which is very different from what you had from having a data warehouse system. It takes years to provision the system. And the other part is it's actually extremely extensible. And what do I mean by that? So one is it supports a variety of very different data types, in addition to primitive data types on traditional databases. It also supports maps and arrays and all of those. And it supports very flexible UDFs, so user-defined functions, and even scripts you could pass in. You could write a script in Python or in Bash and then pass it into Hive to execute as sort of a UDF. It supports a variety of serializers and deserializers, which means it can work with different kind of input formats that even the database itself doesn't recognize. So for example, JSON, text, binary, SERDES. And then it also supports different storage formats. So for example, you can read from HDFS, you can read from Amazon S3 and or HBase. So any storage system that actually can implement a storage input format for Hadoop, you'll be able to use it in Hive. So with all those benefits, it does come with one downside, which is it's actually fairly slow. the first time when we started the Shark project, I downloaded Hive for the first time and opened up a laptop and run a query against one of the example tables at 500 rows. And I did a simple group by on it. It took about 20 seconds. Getting this quote from one guy from Facebook, he said it at a Facebook event, a good day is actually when I can run 6 Hive queries. So that tells you how, how long it takes to run each thing in Hive. So now let's come to Shark. Shark is essentially an analytic query engine that's built on top of Spark that's compatible with Hive. And by compatibility, I mean it's actually being able to execute Hive query language, the Hive queries, UDFs and SERDES, and scripts and types and all of those. And it's able to read directly from a Hive meta store to execute those queries, which really means you can actually execute your queries almost without any modifications to the data or the query in the existing Hive cluster. And it actually makes the query run much faster. And also, since we're coming in the Spark land, we allow the users to actually optionally cache this large amount of data in a cluster's memory to speed up query processing. And last but not least, I'll talk about it at the end, is it can integrate with Spark. So you can integrate actually the more sophisticated machine learning applications along with SQL query processing in the same engine. And it's not just vaporware or vapor academicware. It's been used in production. For example, last 2 nights ago, we actually had a meetup at Yahoo that Yahoo was talking about how they are using some of the systems to handle their query analytics. And example uses include, you could put, for example, a BI tool on top of Shark. So you can connect Tableau directly to Shark to do drag and drop BI. Or you could try to reduce the time it takes to generate an analytics batch report. And the other part is, again, integration with machine learning and SQL. When I talk about fast, how much is it faster than Hive? So these are real numbers you have seen in real use cases, that when data's in memory, it's actually fairly likely impossible to get 100x speed up, just like you have seen Spark over Hadoop. And when data's on disk, you can still get significant, substantial gains in terms of speed. And obviously, this is going to be dependent on the data and the query you run, but we have seen these numbers over and over again in production. And this one, sort of a synthetic, actually this is one of the benchmark we ran when we were writing the Shark paper about 6 months ago, or 8 months ago. And this is taking about a sample of some data from the company Conviva, which does video analytics. And then we took some of the most frequently run queries. So this is the 4 queries that are frequently run in their warehouse, Hive warehouse. And we tried to run it on Shark on 100 EC2 nodes. And as you can see, it's almost, so the blue line is when the Shark's data is actually in memory and you run those queries against those data. As you can see, it's almost impossible to tell how long it takes. So I can tell it takes about a second for all of the 4. Versus when data's on disk, it takes about like 10 seconds. And you can see how much longer it takes for Hive to execute these queries. So now I'll give you sort of a quick introduction of Shark, and you know what roughly it is. Let's talk about how you can use it. Start with the data model. Since about half of you haven't really used Hive, I figure I would introduce you to the basic stuff with Hive. So a large part of this section, the usage, is actually shared between Hive and Shark, because Shark is compatible with Hive. You can literally read up a lot of the Hive documentation to understand how you can use it. You can use Shark. So the first part is data model. So again, this is sort of a database. You will have different tables. And tables represent what you typically mean, actually, tables. And then a slight sort of difference between Hive and the usual sort of databases is within each table, you have partitions. And partitions are basically columns that are range partition within the table. So for example, you might have a table of, say, your traffic log of your website. And each of the partition can represent only 1 week of the data. So let's say you have 1 year of data in a table. For each of the, you might have 52 partitions, and then each partition takes about 1 week of data. And then in Hive, there's also the concept of buckets, which are hash partitions within the range partitions. Shark actually doesn't support that those yet. In terms of data types, there are sort of primitive types and the complex types. And the primitive types include what you would typically imagine. So strings, ints, floats, and all of those. And complex types includes sort of structs, which are basically structures that consist of different primitive types. And then there's arrays, and then there's maps, so this is basically key value pairs. And the Hive query language itself is basically a subset of, I would say, it's an overlapping subset of the SQL 92. And it contains the usual projection, selection, group by. I'll show you an example in a bit. You can do sorts, order by, you can do joins, and you can do some subqueries and union group the queries. And there's a couple specific things about Hive that you're actually able to have this transform syntax so you can execute scripts, which I think when you get started with Hive as a beginner, you usually wouldn't use this. So let's not go too much into it. But one example of how you want to analyze data is actually you can create a table. So very different from traditional database in which you need this huge ETL process to load the data into a database. In Hive, you actually point the table to some external location. So in this case, we're creating an external table that's just from 5 fields, and we're specifying the row format of it, meaning it's actually text format that's going to be delimited by tab. And I'm pointing a location, which in Amazon, it's stored on Amazon S3 in a bucket called Spark Data. And then you can start running queries against it. For example, you can do a select simple count. This is what Matei have done for the Spark demo, is grabbing how many articles contain the word Berkeley. This is fairly, I think this is fairly standard SQL. There's no point actually teaching you this. But what I'd like to point out is you're able to point to an external table in Hive or Shark. Of course, it might be fairly slow because the way the connections from any of a cluster to S3 is actually fairly limited. It's even slower than on disk. So in Shark, one thing you can do is actually we allow you to cache data in a cluster's memory. And this can be done easily by just using the create table as select command and sort of making the name of the table ending with underscore cache. This is syntactic sugar. There's also a more rigorous and principled way of doing this too, by specifying a table property. But I find in a lot of use cases, it's actually much easier to just say a table underscore cache in the name. Use that bit to actually convey the information the table is cached. And then once the table is cached, you can actually repeatedly query it at a much higher sort of throughput or faster rate, as Matei have demonstrated. You can basically gain a similar factor of speed up when you cache the table. The other part I pointed out before is actually able to integrate SQL query processing with more sophisticated analytics like machine learning. So Shark has this API called SQL to RDD. I'm not sure if you can see it, but it's in the val users equals SQL to RDD. And what it allows you to do is pass it a SQL query, and then you can get back an RDD representing the result of that SQL query. Except actually none of our query execution is happening. It was just sending back the lineage to build the RDD representing the result. And once you get the RDD, you can apply the normal RDD features on top of that. So for example, in this case, I can easily integrate a machine learning algorithm directly with SQL. And this is running in the same system against the same set of caches or workers. And when you get into the exercise today, so we put this down in the exercise, but I want to sort of give you a little bit of hint before that is, one, I think, major usability barrier of Shark right now is actually it requires the users to tune the degree of parallelism for any post-map operations. So Shark relies on Spark to actually figure out what's the degree of parallelism you need for any of the input. But when you get to operations like joins or group bys, that you actually have sort of a shuffle stage. And post-shuffle, let's use the concept of reducers to know what number, to denote the degree of parallelism. You actually need to specify what's the degree number of reducers you want to, for example, to handle a reduce or join or a sort. And this is, and by default, we started with actually, so in my very honest opinion, we started with the dump default, which is 1. So which means you actually don't get any parallelism if you start running a query without changing the setting. And what's worse is you could actually possibly running out of memory if the degree of parallelism is too low when the data is big. So make sure you actually set that when you're running your exercises or before running your queries. This is actually #1 problem in performance tuning for Shark. And it's actually, for those coming from sort of MapReduce land, you might be very sensitive to this number, the number of reduced tasks, because when the number of reduced tasks is high, MapReduce actually behaves bizarrely slow. For example, you set it to 1,000, your query might take hours instead of minutes. So when you give it too much parallelism, it's actually very slow. But in Spark land, what we have found is it's generally okay to set this number to be higher and then lower, because Spark actually has a much lower overhead in launching tasks. It's a much lower overhead in fetching very small shuffle blocks. So it's actually okay to set a higher number. So for example, 50, 100, even 1,000. And last but not least, we're actually working on automating this. So the query engine itself will be able to intelligently figure out what are near optimum value to set without the user having to worry about it. So last part of the talk is on under the hood. So what we have done to actually make it fast and why is it fast? So I think it boils down to mainly 3 points. One is it used fundamentally a better execution engine than Hadoop MapReduce, because Hadoop MapReduce is actually fairly, I think, suited for query processing. I'll expand into why in a minute. And the other part is have the optimized storage format. So in Shark, we actually have a columnar memory store with compression implemented that you're able to basically dump a lot of data into this very optimized storage format. While it's also able to support the more flexibility of reading from arbitrary on-disk formats, just like Hive. And then there's a lot of other optimization we have done. For example, by leveraging a lot of Spark, you can do actually co-partition joins of large tables. This partition pruning and this fully distributed store that if you want to know more, I'm happy to talk to you more about offline. So this is how what Hive looks like in a high-level architectural diagram. It has a meta store. And it has a command line shell and a strip or JDBC server. Basically, the command line shell or the JDBC server invokes query processing from this common interface called driver. And the driver does some standards of, I think, database query processing techniques. Like it has a parser that parses the SQL query to generate AST and applies optimizations on the query plan to actually generate a physical query plan at the end that can be executed against MapReduce. What we have done in Shark is actually we take the Hive codebase as is with a couple very minor patches, and then we swap out some of the components, including the query optimizer, the physical plan generation, and the execution engine. And instead of generating plans for Hadoop MapReduce, it's actually generating query plans against Spark. And then among that, there's a couple other optimizations we've implemented that I won't talk about today. And why is Spark a better engine? So I think first and foremost, it's actually extremely fast in terms of scheduling. In Spark, you could actually schedule a task in milliseconds instead of seconds in Hadoop. And this is actually very important because if it takes, say, 5 to 10 seconds just to launch a job to schedule every task, if my query, how can your query ever possibly finish in less than a second? The other part is Spark actually supports, has a concept of general DAGs of tasks, which means it goes beyond the strict two-phase map and reduce. And having this general DAG of tasks means a single query actually consists of a single job, a Spark job. Instead of, in the case of Hadoop MapReduce, a single query consists of multiple stages of jobs, and each stage has, again, its own scheduling overhead. And then there's a lot of other useful primitives that we explore. For example, the broadcasting variable that use a BitTorrent protocol to do broadcasting, which is much more efficient when you need to do map side join or broadcast joins. And then there's a lot of other higher level APIs that you can exploit. So you don't have to shoehorn a query processing paradigm into sort of what you call a map and reduce only. And the other part is actually memory versus disk. So let's use the query we sort of gave in the beginning, but a slight twist to it. This is a query that shows you the number of hits that contains Berkeley for each of the page, and then we want to just group that by them. And in the case of the MapReduce and Hive, the way you do is this query gets decomposed into multiple stages, and each of the stages is actually writing data out to disk and then reading them in again. for the next stage, which actually result in a tremendous amount of I/O. And this actually becomes very slow. In Spark, most of these operations are actually entirely pipeline in memory, and then just sent across the network. The other point I mentioned was the columnar memory store. So Shark actually employs a column-oriented storage engine for the in-memory tables. For the disk tables, it's actually agnostic about the storage input format, so you can implement arbitrary things. But for the in-memory tables, there's a very optimized column-oriented storage format. And actually, very recently, we merged in a big patch from Yahoo that contributed a very CPU-efficient compression and decompression engine on top of the column store. And depending on workload, we have seen sort of 3 to 20x reduction in size in terms of data when you put it into memory. So this means this will spark Shark.8 release in the probably in the next week or so. You will actually be able to squeeze in 3 to 20x more amount of data in memory, actually without sacrificing any of the query processing time. So the trick here is really the decompression algorithm are extremely efficient that it takes no time to decompress them. And so what I've talked about so far, or everything that's going to be released or already out there that people have been using, or it's going to be released in the next week or so. And there's some sort of longer term plans we're doing that's just listed as ongoing work. So for example, we want to do a fully code-generated query plan that has no interpretation by the JVM that you can actually generate the bytecode to run the queries. If you don't know what that means, it's okay. It just means it's going to be a lot faster in the future. And then this Samuel is going to tell you more about the BlinkDB. So we want to being able to integrate BlinkDB to do sampling and approximate queries in Shark. And then another thing Yahoo is doing is the Bloom filter-based partition pruning. And again, it's okay if you don't know what that means. It means your query is going to get faster without actually doing as much work. And then last but not least, there's a lot of optimization, intelligent optimization that the query processor can do to help us to get a better query plan. We're doing this jointly with a large part of the community. And it's actually fairly easy to get Shark set up, or at least to get started to set up. It takes about only 5 minutes to actually download the thing and put up a single node that you can play with. And then the Spark EC2 AMI actually comes with everything installed already, and also the EMR scripts provided by Amazon also has Shark out of the box. And for a private cloud deployment, you can either use Mesos or Spark standalone mode right now to deploy Shark. And the exercise today, you get sort of, actually let's skip this. And somebody is going to tell you more about the exercise in a minute. And last but not least, you can find more information about Shark on the Shark website, shark.cs.berkeley.edu, or entire code base is actually online that you can read about. And we also welcome patches. Thank you. Questions? Yes, Paul. I can repeat the question.
Yeah. You were kind enough to begin to answer this in email, but just to maybe dig into a little deeper here. Integrating this with streaming, is that actually part of a release roadmap, or is that there was mention of a prototype, and I just wondered what the roadmap.
The question was about integration with streaming, which you're going to hear more about in a minute by TD. I think we have all the dots in the right place to actually make that happen. The reason I didn't put it up in the ongoing roadmap is it sort of brings in, I think, a new type of system that's slightly different from a more typical just SQL workload. But I do think it will happen. And even if we don't do it, it looks like there's enough interest in the community to make it happen.
You were talking in one of your slides about the Columnar organization, I think right there. Now, since everything's in memory, do you have to worry about the the caching issues that we have in the processors in terms of clashing and stuff like that? And how do you deal with that?
Yeah. So
especially
we are. That's a good question. So do we deal with like the more lower level system issues, like what if the cache line clash between? So actually, the whole thing is done in a share nothing way that each task is launched like a Spark task. It runs on a single thread that's basically managed by the JVM. And I think the issue resulting from sort of cache line, say, thrashing is much less when you have a very share nothing system that each thread is treating as a share nothing thread that's handling a scope of data that's local to it. But I think it's a good question that it's possible to dig more into it. Maybe we can get more, squeeze more performance out of it. But I think the ecosystem in general right now has enough other low-hanging fruits that it probably will be a while before we need to really look into this. There's enough other parts that we can improve. And I'm speaking in general in terms of both Shark and a lot of other systems that there's actually a lot of low-hanging fruits out there that maybe at what you worry at the L2 cache level is not the most immediate problem you want to worry about.
All right, since we're running a little bit behind, let's stop questions there and let TD start.